just like with single variable functions, you can also talk about higher derivatives. Now, higher derivatives are more complex because you've got more variables and you have to be careful about what you mean when you talk about which derivatives to take. So you have to be careful with the order. So here's the notation that we're going to talk about. If I have this expression and I write two subscripts fxx, the inner function was first. The outer letter is the second letter here. And this means you're going to be taking an x partial derivative of this thing x. So this outer letter comes out front. This is going to be a second derivative of this function with respect to x. So sometimes we can write it with a 2 up there and a 2 down there. If I wanted f of x, y like this, this means derivative of this function with respect to y. And the function that I'm putting inside was the first derivative. And the first derivative looked like this. And so another way to write this would be a second derivative of this function. The outer one is what happens second. So you just have to be sure. Now I'm going to go through some examples here. And the example that I'm going to talk about is this function right here. Now note, this function is essentially the distance from the origin, 0, 0, to some point x and y. The partial derivative with respect to x, that means I'm taking the partial derivative of this expression. By the chain rule, I'll get a 1/2 x squared plus y squared to the minus 1/2. Now I need to take an x derivative of the stuff on the inside. Of these things on the inside, this y is a constant with respect to x. So the only thing that I care about is the x derivative, and I'll get a 2x here. So this ends up giving me a 1/2, 1 over the square root of x squared plus y squared times a 2x. The 2's will go away, so I'll get x over x squared plus y squared. Now similarly, if I wanted the y partial derivative of this expression, I would have to take the y derivative of x squared plus y squared to the 1/2. I need to use the chain rule again, so I'll get a 1/2 x squared plus y squared to the negative 1/2 times the y derivative of the stuff on the inside of the root. Now, just like before, this is a constant with respect to the variable y. And at the end of the day, this expression will just end up giving me a 2y. So I'll have a 1/2, 1 over the square root of x squared plus y squared times a 2y. 2's will go away, and I will now have a y over x squared plus y squared with the square root. Now, when it comes time to second derivatives, we need to go a little further. So if I were to write uxx, this would mean the x derivative of the first partial derivative with respect to x. Well, the first partial derivative with respect to x was this function right here. I'm going to rewrite this in such a way that I can calculate this a little more straightforwardly. So I'm going to write this using the product rule. And so the term in the bottom will end up having a negative power but be a multiplication. I'll have an x partial derivative of the first times the second plus the first function times the x partial derivative of the second. So this is going to end up giving me a 1 x squared plus y squared to the negative 1/2 plus x times a negative 1/2 x squared plus y squared to the minus 3/2. And then I have to take an x derivative of these things on the inside, just like before. So this will end up giving me an x squared plus a y squared to the negative 1/2. I'll have an x with a big bracket here, negative 1 over 2. I'll have this stuff to the power of 3/2 in the bottom, multiplied with a 2x. These 2's will go away. I will now have 1 over the square root of x squared plus y squared minus x squared over x squared plus y squared to the 3/2. Now, it's going to be important that we get comfortable with finding lowest common denominators. And this term right here ends up being the lowest common denominator. So that means I need to multiply everything in the first expression by x squared plus y squared, top and bottom. When I put everything over a common denominator here, what you'll find is that those terms will cancel out and I'll get a y squared, x squared plus y squared to the 3/2. So this is what the second partial derivative is with respect to x's. So this is what we might call a pure second derivative because it's with respect to the same variable twice. Now, similarly, if I wanted to calculate uyy, I would be calculating the derivative of uy with respect to y. And you could go through the exact same process, and you will find that you'll get this expression. So they almost look identical, save for the term upstairs. Now, again, these are called pure partial derivatives, or pure higher order partial derivatives. What we're going to talk about are what are called mixed partial derivatives. That's like saying the following: uxy means take the y derivative of the first derivative with respect to x. So that means take the y derivative of this expression that we got, x over square root x squared plus y squared. With respect to y, this thing is a constant. And that means I can take it out right away, and I'll get x and the y partial derivative of x squared plus y squared to the negative 1/2. There's no more product rule. I can go straight to the chain rule, and I'll get x times negative 1/2 x squared plus y squared to the negative 3/2 times the y derivative of these terms on the inside. X times negative 1/2 1 over x squared plus y squared to the 3/2 times a 2y. Remember that the x is a constant. These 2's will go away, so I'll end up getting negative xy over the square root of x squared plus y squared to the 3/2. If I write uyx, that means take the x derivative of this expression uy. And that means take the x partial derivative of the expression that we got, which was a y over the square root of x squared plus y squared. Now, just like before, this is a constant with respect to the variable x, so I can immediately take it out and then simplify the way in which I'm going to write this derivative. So I'll get an x derivative of this term to the negative 1/2. I can use the chain rule immediately and get a negative 1/2 all of these terms to the negative 3/2 times an x derivative of this expression x squared plus y squared. Now this is going to give me a 2x because the y is a constant. This 2 and this 2 will cancel out. So I'll get a negative xy over x squared plus y squared to the 3/2. Now this was exactly the same as what I found for u of xy. Is this a coincidence? And it turns out that no, it is not a coincidence. So there's something called Clairaut's theorem. And Clairaut's theorem has to do with mixed partial derivatives. And it says let f of x and y be defined on some set D in R2. So it's a two-variable function. If these mixed partial derivatives, fxy and fyx, are continuous on D, so they are continuous functions of x and y, then the mixed partial derivatives will be equal. On all points of D. So this is in fact the guarantee that we were looking for. It is not a coincidence that those expressions were the same. Now this can extend to multivariable functions with more than two variables and also to higher derivatives, higher mixed partials with the appropriate continuity. And what that means is things like fxxy would be the same as fxyx would be the same as fyxx. And in the example that I did a little earlier, when I had this expression here, x squared e to the yz, remember that fx was 2x e to the yz, fy was x squared z e to the yz. If I wanted fxx, I would get 2 e to the yz. So if I wanted fxxy, this would give me another 2z e to the yz. I would just use the chain rule like before. If I wanted fyx, I would get a 2xz e to the yz. And if I wanted fyxx, I'm just taking an x partial derivative of the above, which means these two things are the same as expected.